All right, so this talk is for Baz. I know we've been going back and forth about white dwarfs for some time, and it's confusing to me, to be honest, because white dwarfs they're about a solar mass, and then they expand to becoming a blue giant, which has multiple solar masses. It's very odd because they weren't gaining mass as much as they needed to gain mass to get the size of the blue giant like Bellatrix. And I wrote this paper, it's up on Vixra. I'll read it out to you and I'll go ahead and explain my ideas behind it. Conservation of mass limits in white dwarfs. Now, conservation of mass basically means a system that's closed off to exchanges of heat and exchanges of matter. A closed system is something that's going to remain the same mass. You can't make it more massive or less massive. Think of like a cheeseburger in a black box. You're not gonna put light, you can't put light onto the cheeseburger, and you can't throw more pickles or ketchup onto the cheeseburger. The cheeseburger is gonna have its mass conserved. And what I'm saying is, with white dwarfs, think of the white dwarf as the cheeseburger. The cheeseburger can increase in mass without any external mass added to it and without any external light and heat energy added to it. So basically, the cheeseburger can become more massive. And that's a big no-no in all of physics. You're not allowed to question the conservation of mass. If you start questioning it, you get labeled a crank and a crackpot and whatever. And there's a lot of social pressure towards challenging established what they consider to be facts of nature or laws of physics or whatever. But as you'll see here, we have a different universe than what the astronomers and physicists and all the, dare I say, dogmatists believe. And it's really hard to change a lot of the basic laws, but anyways, here we go. It is hypothesized that mass is conserved in closed systems, but there is a caveat to that due to white dwarfs. In the general theory, white dwarfs have masses not conserved, meaning if you take away all the transfers of heat and matter away, it will become more massive as it transitions to more massive stages of evolution. This means mass is not conserved under extreme pressures and temperatures. In short, there are properties of mass that we do not understand yet, and white dwarfs show this. In the general theory, white dwarf is about the diameter of the Earth and has the mass of the sun, so we're talking extremely dense here, if not a little bit more for each property. This means white dwarfs are extremely dense, far beyond our regular familiarity. We're not familiar with white dwarfs, how dense they are. It's far beyond our imagination, trying to imagine how dense this thing is. This is problematic though, because there's not a lot of extra heat or mass that can be added to a white dwarf to make it expand into a blue giant. This being said, it follows that the property of mass is gained in the white dwarf as it expands regardless. This means that a white dwarf creates its own mass and it can be created and destroyed. But if that is not how people would like to word it, I guess mass effects can be dimmed and brightened. This is counter to all experiments done on the Earth, but there is an explanation. What I'm saying is, it isn't that mass conservation isn't true under normal conditions. What I'm saying is that if you increase the conditions, if you make the conditions extreme, then the conservation of mass goes haywire. And I give a few examples here. The laws of physics and chemistry as we understand them in our regular life do not apply when matter is subject to extremes in many cases. And to any physicist that's listening to this, you guys know better, okay? Listen, superconductivity, the ability for electric current to flow totally unimpeded. There's nothing in physics that predicted that happening, okay? That's when material drops to very close to absolute zero, and it can have electric current flowing through unimpeded forever, essentially. That's totally weird. Superfluidity, the ability for fluid to travel uninterrupted even up container walls. So say if you have a glass of water and the water is a superfluid. It'll flow up and out of the glass. that's totally weird. Special relativity, where time and space become interchangeable when traveling near luminal velocities. That's completely weird too, completely out of our daily experience. But it's true. When you approach the speed of light, the space in front of the craft contracts, and it doesn't take that long to get from here to there, as long as you travel close to the speed of light per unit. So I'll get to that in a second. Now I have here, the natural world is very peculiar. Notice how the word has the word liar at the end. Mother Nature is constantly lying to us. She tells us things via experiment, yet simultaneously hides the truth from us. She both hides the truth and shows the false. So she has simulation and dissimulation. It's basic counterintelligence. It takes a clever investigator to see through the deception. In short, it is not that conservation of mass is not a valid property. It is only valid under conditions that do not involve extreme temperatures and pressures, that which occur in white dwarfs and birthing galaxies, quasars, radio galaxy cores, that kind of stuff. And it has something to do with the gravitational field, which I'm going to put that on the back burner for a little bit longer. There is a stability to the property of mass when matter reaches a certain threshold of calmness. It is not being compressed greatly nor being heated greatly. The idea is that mass does, in fact, arise and can have its effect negated. It can be both dimmed and brightened like a light bulb on a variable switch. And here I'm going to explain light. As well, the mass effect becomes only variable as you approach the limit. Now, I'm not too sure where I'm going with this, but essentially I'm going to explain it in terms of special relativity here. If you travel 99.9% the speed of light, you're going 10 times faster than 99% the speed of light. It's not like miles per hour. It's not like you're traveling 99 miles an hour down the road, and if you go 99.9 miles an hour down the road, you're just going a little bit faster. It's not like that with light, especially when it's approaching the limit. And that's the mass effect issue I'm concerned with here. As you approach some sort of limit with extreme temperatures and pressures, which white dwarfs signal, there are effects that mass has on top of the gravitational field which lie to the astronomers. And they're being deceived because they believe white dwarfs only have the mass of the sun. What I'm saying is, in the general theory, their mass is actually a lot greater. In essence, the white dwarf is not only extremely massive, it's more massive than what they predicted it, or what they have it as being. So I'll get to that in a second here. To throw some numbers in here, Bellatrix, one of the stars in the Orion constellation, is a blue giant with about 8.6 sun masses of material. In the general theory, white dwarf is one solar mass. So in essence, 7.6 sun masses of material will manifest out of a white dwarf so that it expands and has the mass of Bellatrix. In real-world terms, a race car, about 860 kilograms, could have its mass negated down to the race car weighing about 100 kilograms. This is not just the race car, though. It is the entire car plus the person in it. So given the person in the car is part of the 860 kilograms, they're about 80 kilograms, he or she would weigh about 9.3 kilograms, given the entire mass of the race car is negated that much. This would be a huge effect, but definitely more mild than extremes needed for extreme acceleration, such as the craft witnessed by Commander David Fravor of the Tic Tac UFO. If you guys want to watch that video, look up Commander David Fravor. He was attached to the USS Nimitz, and he had observed the Tic Tac UFO doing extreme maneuvers, and it was pretty crazy. It's a pretty crazy video. You guys should find it. If you remove 99.99999% of the mass effect, then you can accelerate the craft as if it were photons coming out of a laser. So there are extremes. There is slight mass effect removal, medium to heavy to extreme to total. And the more, as you approach getting rid of the mass effect, the more mass you can remove. So, for instance, okay, I'll just go and keep on reading this. This is not to say the car needs to travel any faster or slower, but that its mass can be dimmed without needing to even do any of that. As well, the mass can be increased too. Think of Thor's hammer. Only those worthy of ruling Asgard can lift it. What use would that have? Well, a mass centering device could be placed in the craft to make sure people would have the effects of an ancient star, the gravitational field, to make sure their lymph nodes are fully functional, the drainage is good to go, their skeletal structure is, intact, the fluid in their eyeballs remains on level ground so they don't go blind, that kind of stuff. This would ensure health and well-being for a very long-term space travel. And that's what I believe we're going to be doing. We're not going to be doing the gyroscopic spacecraft where they spin to create the effects of mass gyroscopically. What we're going to do is we're going to figure out how to dim or increase the mass effects for certain areas, for being able to move both the craft and keep the occupants in it on an even keel when extreme acceleration takes into effect. For instance, if you're traveling, if you were to put a human body under like 100 G's of acceleration, the mass is what gets to you. If you remove the mass, then a 90 kilogram person such as myself, if you can get me down to maybe a gram, of mass, then you can accelerate my ass down like a bullet coming out of a rifle, and that is what that's what the future has in store for us. I think that's the future of physics. But in order to get there, we have to start questioning the basics, the things that we believe are solid, that aren't going anywhere. We have to start questioning them and sort of looking beyond them and looking at those assumptions. But conservation of mass is one of the real big bugs that I've been bothered with, especially with development of this theory, because I have white dwarfs in the beginning, and well, you guys know the whole story behind that. But in essence, what's happening now is the giant dam that is preventing us from understanding how to travel to the other stars is not our ability to create propulsion. We have that down already. We get it. We have ion propulsion. We have various other advanced technologies. Our problem is that we have specific laws that we say are impossible to get around, yet white dwarfs lay out on the line. They're actually much more massive. It's very strange though. They are already extreme densities, and I'm saying that they're actually vastly more massive. And that they are giving us a clue while simultaneously lying to us. Astronomers have the approach that white dwarfs are already too heavy to understand, and they leave them alone. They say, nope, they're heavy enough. Let's design entire models around them and ignore other possibilities. And that's a big problem with astronomers these days, is that they just look at what's there and then they design entire things around what appears to be. They are very appearance oriented. They don't have the creativity to see through what appears to be and to look at the stars in a creative light, because graduate school kind of just nails the crap out of them and makes them all blockheaded from the very beginning. So I don't want to talk about that, but anyways, I wrote this paper to sort of just open up people's minds to other avenues of approach for solving these mysteries. And as well, the other project I'm working on, I just wrote this down when I was in my car and I pulled off to the side of the road and parked in the parking lot. And I wrote this down, but there's going to be a way to determine the ages of stars via thermochronology. So how much heat the star produces can also be used to determine how old it is. And we could probably also use thermochronology to determine how old white dwarfs are and very, very, very young stars, where a lot of the birthing processes are they need to be studied. But you have gyrochronology, now you have thermochronology, and there's another one, I can't remember what it is. But anyways, I think I made this talk way, way long enough. Alright, there you go.